Okay, good morning. Um, Let me start off. So today is lecture 4. Um, I have just sent out an email to all of you, so maybe some of you have seen it. Um, so important announcements are, like I said, I'm going to keep all course communications in this course through Piazza. So move from now on, all my emails to you, or it won't even be emails, all my messages, course communications will be from Piazza. And I think everybody has got enrolled, right, into Piazza. There's just one person who needs to do it. So basically communications. The second is that I have updated the syllabus. So if you go to Moodle, you will see this syllabus link has been updated, and basically what that is the first few pages are the same as before. So the first few pages and the general instructions are the same, and then after that I've added a page of planned lecture material, lecture contents. Take a look through it just so you are aware of what is coming up. And then I've got a planned course schedule. It's basically a calendar that says what is due when. I've tried to put as many of the due dates as possible. You won't be able to see it now, but if you open it up on your own, you will be able to see it. So for example, today we are on the 29th, right? So basically this week we are going to do lectures 4 and 5. This week you should be working on quiz 1, which I've posted, and you should start homework 1, which I'll post soon. So for example, quiz 1 will be due on Sunday, the Sunday coming up at midnight. So almost everything is going to be due on Sunday at midnight, all due dates, except in the very end of the course, just because the finals comes up, the quiz 7 and project 2 will be due on, I believe this is Friday. So that and the finals will also be due on the next Friday. So except for those two, everything is going to be due Sunday at 23:55. Yes.
We probably know, but would you consider moving it to Monday since it's a holiday weekend? It's Labor Day this weekend.
It's only a quiz. It's a 45-minute quiz.
Okay.
I just don't want to interrupt the flow of Sunday deadlines,
No
so that
worries.
I think you're all going to be hopefully tune yourself every Sunday. You know, not every Sunday has a due deadline, some submission deadline, but if it's a Sunday, you should be at least checking to see, hey, have I missed something for today? So the quiz is a 45-minute. It's like a 5-question quick thing that we are doing at this time. Like quiz 1 will be lectures 1 through 4. So the first 4 lectures and the syllabus. So from this material there will be 5 questions. It's a timed 45-minute quiz. I mean 45 minutes should be ample, but I just want to have a time restriction. So the idea is that you don't accumulate on the lecture material and start watching 8 lectures before the homework in order to do the homework, right? So just it's a way to make students sort of keep up with the material as we go along, and it's not like super hard or something. I mean 1 or 2 questions may make you think, and it's low stakes too. So if you miss a question in a quiz, you shouldn't really be worried. Do you have a question?
I guess my main question was, the quizzes, does that mean we have to take them on Sundays, or?
No, you can do it
anytime? Okay.
correct. So the quiz is now open. and it's through lecture 4, so today's material. So after today's lecture, you can go anytime before 23:55. You should submit by 23:55 on Sunday.
But once you start, you have 45 minutes.
Yes, once you start, it's a timed 45-minute test. So you can't start the quiz and then start going and watching lectures, right? That's just that's all the idea is. And so that's what this calendar has. Of course, some things are going to change as we go along. Maybe there will be some material that I don't end up finishing, and we might postpone something by a little bit or something like that. So, but this is the plan. Okay. The other thing is, I wanted everybody to complete this FERPA consent form, which I need for you to do the blog posts. I think almost everybody has done. Maybe a handful of people haven't done that. It's already past due. It'll only take a minute, so just go ahead and do it. Okay, so the more you postpone it, the more chances are that you will forget to do it. And if you scroll down, there's the quiz. So if you start it, you'll have 45 minutes to complete it. And yeah, so let's go back to the document camera. So this calendar is pretty important. Like I said, I anticipate following it as much as possible. So I would even recommend printing these 4 sheets or something and keeping it at your desk or wherever your workplace, so you can constantly, you can refer to it easily. If not, it's on Moodle. So just go to the syllabus. The last few pages are the calendar. Quiz 1 has been posted, due on Sunday, 23:55. So I won't be reviewing these deadlines for every quiz throughout the course. That's what the calendar is meant for, right? But usually I'll send you a message on Piazza saying, hey, quiz 2 is posted, it's due at this time. And after that, I won't be sending reminders. It's really, you should keep some calendar or some other memory aid for it. If you miss a quiz, it's gone. I mean, it's just too much hassle to go and reopen a quiz just because somebody forgot. So the point is, don't forget. It's just a 45-minute, pretty easy thing. Go ahead and do it, and keep some kind of reminder for on your phone or something. I've posted a self-introduction on Piazza. If you can reply to that with just introducing yourself, that'll be a good way for all of us to know each other. And there was one more thing. Yeah, the FERPA consent form. Take a minute to complete it. So unless you do this, I can't let you do the blog posts. Okay. Any questions? So homework 1 I'll be posting very soon, maybe today or tomorrow. Meanwhile, if you're rusty on your programming skills, you should be working on brushing up programming skills, because homework 1 will require a little bit of programming. Okay. So in the last class we talked about CP distribution. Right, so this is from page 3-11. So this was an example CP distribution, and main thing is it's plotted upside down just so that it looks similar to the velocity distribution, and it will let us think about those two plots in the same way instead of having to flip your thinking with one plot or the other. So from the CP distribution you get pressures, and that's where we kind of stopped. So positive CP means it's a positive pressure, so it will press on the surface, and we have dF equals minus P dA, where dA is the elemental area vector pointing along the outward normal. Okay, so now let's see how we can proceed and calculate lift and drag and all those things. So first let's look at a pressure distribution on an airfoil in inviscid flow. This is just going to be a very representative pressure distribution. So it's not like it's always going to be like this. It's just for some airfoil at some angle of attack. And of course it will change for different airfoils and angles of attack, but this is just a representative one. So let's say here is an airfoil. And let's say this is V infinity, this is angle of attack, and I usually draw this angle pretty large so that you can see it clearly in the graphical sketches, but this is a very large angle of attack. Usually angle of attack is something like 0 to 12 or 15. Okay, so you might have a pressure distribution like this. Okay, so this might be some pressure distribution. So this is an inviscid flow. Inviscid flow means no viscosity, which means no boundary layers, no drag. And as we shall see later, inviscid flows are a very useful approximation to study many airfoils and wing flow situations. So although they differ from reality, they are a useful sort of approximation for many cases. So this this pressure distribution will end up causing a resultant force, and this resultant force will be something like this. And in inviscid flow, this resultant force will also act at an angle of alpha from the vertical, and this R is equal to lift. So R is the resultant force, and this is the force you will get if you integrate all these pressures, and this is equal to lift And lift by definition is the component So this is important to remember. We have a resultant force and the component of that resultant force in the direction perpendicular to V infinity is called lift. You will come across some situations, maybe not as much in this course but in other places, where you will wonder what lift is. Lift is always the component perpendicular to V infinity. In inviscid flow, the only force acting is lift, there is no drag. So the resultant force itself is the same as the lift. Now viscous flows are going to be different, so let's see what it looks like in viscous flow. That is, this is the more general case which means, in other words, this is a real flow, not an approximation. So in these viscous flow cases, we will have both pressure and shear acting on the surface. So in the earlier diagram we had only pressure, but we'll have now shear force as well. And even the pressure distribution so in inviscid flow, if you integrate the pressure, you get purely lift, no drag. But in viscous flow, if you integrate the pressure, you will get not just lift but also drag. So this is called pressure drag. That is, there is pressure drag. Okay, so if I take an airfoil for example, you will not only have pressures, but you will also have shear stress. And shear stress is basically the frictional type of scrubbing kind of stress. And this is represented by symbol tau. And this is the pressure distribution. And on any body, all the aerodynamic forces come from the pressure and the shear. These two are the real only sources of aerodynamic forces. Excuse me. So, if you know all the pressure distribution and the shear force distribution, you can integrate it to get the forces and moments, which is the programming assignment in homework 1. Okay. So what happens in viscous flow is there is now lift and drag. So let's plot the force diagram on an airfoil in viscous flow. So we have an airfoil here, V infinity, and this is alpha, and let me draw a vertical line, and then let me draw perpendicular to the V infinity. So this is this line is supposed to be perpendicular to V infinity, so this angle is alpha. May not be perfect, but it's just a sketch. Okay. So in viscous flow, we'll get both lift and drag. And so the resultant force will be a vector addition of lift and drag. So you might have a resultant force that looks like this. Yeah. So we'll call this R, resultant force. So by definition, lift is the component of this resultant force perpendicular to V infinity. So you take this resultant force, this is the perpendicular to V infinity. So you have a component perpendicular to V infinity and parallel to V infinity. So this is lift and this is drag. So R here is resultant. D is drag, and that's along V infinity. In some situations, it's also convenient to decompose the total force, the resultant force, into normal and axial forces. And so normal to the chord and along the chord. And I'm going to call that X and Y. So let's call this the X axis, and the Y axis is here. So I'm going to call this the Y force is this. Sometimes it's called normal force with a symbol N, but really it's just different symbols. It just means the same thing. And this force is called X force or or axial force A. So let's write these down. Y or sometimes N is equal to the normal force that is perpendicular to the chord, and X, or sometimes called A, is the axial force along chord and usually you will call X force positive along the X axis. So the X force as shown above is negative, right. So in this particular sketch the X happens to be in the negative X direction, so it's negative as shown in the sketch. So one of the things you see here is X is actually pointing towards the leading edge, which is, think about it, that's it takes some time to get used to it, right. That means there is a force, and this is a completely sort of legit force. This is a good resultant force for an airfoil. This is a normal kind of, this is not just a sketch, this can happen. And so there is a force that's driving the airfoil forward. So if it's an airplane flying in level flight or something, or if it's an airplane in level altitude, it's the airfoil pressure distribution itself is pushing it forward. So do we need an engine? Why do we need a propulsion system? I've asked you in different classes, so some of you probably are clued into what I'm saying. So we have a force that's aerodynamic force that's pushing the airfoil forward. What's going on? Why do we put engines on airplanes if we can do this with just aerodynamics? Okay, I'll open it up to those who have probably heard this in other classes. What's going on? Those of you who have taken applied aero, or I think we maybe talk about it in wing theory, or in Aero 1, other courses I've taught. Yes.
The resultant force is kind of pointed back from the free stream velocity. I don't know if that's it or.
Right. So this is just the way we are orienting the picture. We are drawing this picture with chord line horizontal, and we are saying normal and axial forces are perpendicular to the chord line and along chord line. Chord line is not the direction of flight. What is the direction of flight in this picture? It's opposite to V infinity. So the airplane is actually flying like this. We have just for convenience tilted it to make the chord horizontal. So this is, if this airplane was flying horizontally, let's pretend that this airfoil is an airplane. The airplane, if it's flying horizontally, the airplane will be tilted up, right? So the chord won't be horizontal, the airplane will be like this and flying this way. So just to sketch, this is actually a situation where the airplane is like this. So this is, and then it's flying this way. And it's at an angle of attack of alpha. So when we say there is a component of force along the chord line, so it will be along the airplane, and so that's in this direction. That's not in the flight direction. and there is a component normal to the airplane and along the airplane, and those two will cause a resultant force that will be like this, and this resultant force does not have a component along the flight direction. So if you resolve it along the flight direction, you will have a lift. I'm not drawing this too well, but there is actually a drag, and the drag is opposite to the direction of flight. Right? So it doesn't mean you don't need an engine, because the airplane is flying like this, and if you want to maintain altitude and if you want to maintain speed, you need a thrust force that will act in this direction. It's in this particular sketch, it's a small thrust force, but nevertheless you need the thrust force. If you don't have the thrust force, the airplane will either decrease speed if you try to maintain altitude, or if you try to maintain speed, it will descend, and both of those are perfectly okay. But if you want to maintain level flight at this velocity, you need thrust, because there is a drag acting opposite to the direction of flight. So it just gets confusing, because in many situations for convenience we plot this whole thing with the chord line horizontal, and then if you do all the forces, you will get a force in the forward direction, and chances are at some point in your career, this may be 8 years down the line when you've sort of forgotten this discussion, you'll be doing some work. If you're going to be working in aircraft aerodynamics and so on, you'll be doing something like this, and you'll get a forward force and you'll wonder where you went wrong. It's actually perfectly fine. So just try to remember it. Remember this. Okay. So most of the time we don't use actual forces, we use force coefficients. So let's introduce the lift coefficient, which is what we'll use this a lot. So the lift coefficient is written as C subscript L, coefficient of lift. So half rho V infinity squared is the free stream dynamic pressure. This is the lift, and this is the reference area. So S ref is reference area for a 3D body. When I say 3D body, this is like a wing or airplane. And for wings and airplanes, S ref usually is the planform area of the wing. So if you have a wing like this, this is the wingspan. And so this is the planform area. So C average is the average chord, and this is the wingspan. So S ref is also, you can write that as S wing, and sometimes it's just written as S. People know this is capital S, and we usually use that for wing area. So this is for a 3D wing. This course is about airfoils, which is the 2D slice of a wing. So we do something slightly differently, but it's connected with what we are doing for the wing. Sorry. So an airfoil is really is a wing of infinite span. So it's really, if you take a wing and goes to infinity on both sides, so infinite span, we take a slice and we look at the flow in this slice. So this, and this slice has got 2D flow. And the flow is 2D because you can take the slice anywhere you want along the wing, it will be the same, right? So it's two-dimensional flow, there is no change in the span-wise direction. So to consider the loads on an airfoil, you have to have a certain amount of span because you need area for force, for pressure to act and cause a force. So to discuss loads on an airfoil, we usually consider a unit span, a span of 1. So in other words, B equals 1. And so the wing area becomes B times C, and that's equal to 1 times C, that's just equal to C. So now if we want to define lift coefficient, you have to think about a span of 1, and so it becomes like this. So airfoil lift coefficient, this is different from wing lift coefficient in certain ways. So this is written as C subscript small l, and that's equal to lift over a unit span, lift on a unit span of a airfoil, divided by half rho v infinity squared times, earlier we had wing area, so now we have C times 1, and this is B equals 1. And so the important distinction here is lowercase l is used for 2D flow. Another way to think about the airfoil lift coefficient is you can write this as L prime over half rho V infinity squared C, where L prime is lift per unit span. So these two are the same thing. So this has, so L prime has units of force divided by length, that is Newton per meter. So just like lift coefficient, there are there is drag coefficient and there is pitching moment coefficient. So in a similar manner, C subscript small d is drag coefficient in 2D flow. So this is drag per unit span over half rho V infinity squared times C. And Cm, C small m is pitching moment coefficient in 2D flow again. Right. So is there a problem here? Yeah.
C squared.
Yeah. So if you think about it, this is moment per unit length, and if you look at this dimension, it won't be moment per unit length. So you really have to have squared, C squared. So this is a very sort of typical mistake people make. We will be working with lift and drag coefficients a lot, and we'll always be writing half rho V infinity squared C here in the denominator. But then when you go to moment, you need C squared. So you'll forget that because you're doing half rho V infinity squared C here. Remember, moment, to non-dimensionalize that, moment per unit span, you should have half rho V infinity squared C squared. These are just like definitions. So here d prime is drag per unit span, and m prime is pitching moment, actual physical pitching moment per unit span. For a 3D wing, for 3D cases, wings or aircraft, pitching moment coefficient is slightly different. It's written as C capital L, just like CL and CD for 3D. C capital L is for pitching moment coefficient, and that is moment of the for the whole airplane or wing divided by half rho V infinity squared divided by S ref times C ref. So in wing theory, for example, we'll be using something like this, or in airplane flight dynamics, this is what you use. So in our course, we'll be dealing with 2D flows, so we'll just stick to this part. Okay, so what is pitching moment? So lift and drag are fairly familiar. Let's just quickly review what pitching moment is. So in the earlier picture, I drew an airfoil and then I drew a resultant force. Usually, in addition to a resultant force, there is a moment that accompanies the force, and this moment is called M, and this is the pitching moment. It's called pitching moment because in an airplane it pitches the airplane up or down, right? And its value depends on the reference point used. In our case, this is the reference point. Reference point is just another name for the axis about which the pitching moment acts. So this is the axis in this picture. So the force and moment are positive as shown. So this is the positive direction of pitching moment. Nose up is positive. That's just sign convention. So because the pitching moment depends on the axis location, we have to say about what axis we are looking at the pitching moment. In other words, we have to specify the reference point. So for example, we have to say are we talking about moment about the leading edge or moment about the quarter chord or moment about, which is also written as, quarter chord is also written as QC. Sometimes you look at M about the half chord or trailing edge or so on. So just saying moment, pitching moment is some value is not complete information. You have to say about what point the pitching moment is written. Okay, we'll be looking at this in much more detail as we go along. So this will start to become familiar when we apply it to some examples and cases. Okay, so one of the first exercises is to calculate lift and pitching moment and drag from a velocity or CP distribution. So let's spend some time talking about that. Any questions so far? So an early exercise will be to integrate the CP distribution and compute lift and pitching moment and also drag. So we are going to take some airfoil and we are going to take a small portion of the airfoil that we'll call a panel. So this is just a panel of the airfoil. And we'll just call the panel as going from point 1 to point 2. And this point has got coordinates x1, y1, and this point has got coordinates x2, y2. And let's say the pressure on point 1 and 2 are P1 and P2. So if we assume they are positive pressures, they'll press on the surface, so they will cause a force downwards, and so you'll have a pressure distribution something like this. So this is P1, this is P2. Okay, we can assume that the panel is flat, is small and flat. So in reality the airfoil surface is curved, but if you divide the airfoil into lots of little panels, you can assume each one is flat for the purposes of integration. And so even though the surface may be curved, we'll assume it's a flat panel, and we have P1 pressure here, P2 pressure here. I'm just drawing it in large scale outside so we can look at it more clearly. So for purposes of integration, again, if you divide the airfoil into lots of panels, you can assume that an average pressure acts on this panel, and the average pressure is this. A uniform constant average value acts here, and that is P1 plus P2 over 2. Okay, so with this we can start calculating the forces. So let's look at this one panel in good detail. So we had the panel here. This is point 1, this is point 2, and this is P1, this is P2, and we are replacing it with an average. And this is P1 plus P2 over 2, and this is the airfoil surface. And this distance is ds. D is for a small element, and S is the the arc length along the airfoil. So, and let's say this angle is some angle theta, the angle formed by the normal to the panel with the horizontal axis. So let's say there is a force dF acting on it, and I'll draw force like this. dF is the force acting on this panel due to this pressure. So what is this dF? With all these things that we know, can you say what, can you write the expression for dF? Yeah, but that will be, okay, let's write it out. P1 plus P2 over 2 multiplied by ds, but this is not units of force. Pressure times length is, you need usually pressure times area, right? So what's going on? Yeah, times unit span. So airfoils will always consider a unit span in the span-wise direction. So let's call that dz. So this is, well, we'll put a dz and then we'll put dz equals 1, right? So this is span-wise width of the panel. So for convenience, we assume dz equals 1. So let's put this in the xy axis system. So we have x here, y here, and we have this flat panel that goes from 1 to 2. And this distance is ds. This distance is dx. So dx is x2 minus x1. And this distance is dy. dy is dy equals y2 minus y1. Okay, in this illustration, dy is negative. So um, so we have this force dF. We want to decompose that along the x and y directions. So let's write the x component of the force as d capital X. And we'll call capital X as the component along the positive x direction. And like that, dy is the y component of df along positive y axis. So the reason, this is just the usual differential kind of notation. So df, d capital X, d capital Y are elemental forces on the panel, and we are saying elemental because the panel is a small element of the airfoil. So when integrated over the whole airfoil, or you can think about it as summed up in a discretized fashion, you'll sum it up. So when integrated over whole airfoil, we get the total force F, the x component and the y component forces. Okay, so in the previous page we wrote df is P1 plus P2 times ds times dz, and we are just going to stop using dz because we always set it to 1. We can now decompose the df into dx and dy, right? So what will it be? If this is theta, what will dx be? Df cos theta. So let's write that dx, d capital X is df cosine theta, and if you further want to write df in terms of the pressures, it will be P1 plus P2 over 2 times ds times cosine theta. So now the question is, will this be plus or minus? And therefore will the plus or minus be carried over here? So here in this particular case, dx will turn out to be in this direction. So you've got to think about it a little bit. I'm not going to say it's plus or minus, but just something to be careful about. So it turns out, let's keep carrying the plus or minus ambiguity some more. So you can write this as P1 plus P2 over 2 times dy. Right? Does it make sense? Why can we write it like this? Yeah.
ds cosine theta is equivalent to dy.
Yeah, so ds cosine theta. So theta is the angle between horizontal and the normal to the panel, and that will mean vertical to the panel. So this angle is theta. So ds cosine theta is actually dy. So I mean usually it's I think preferred, and it causes less numerical error to not handle angles. If you can handle displacements and lengths, it just works out better most of the time. So that's because dy equals ds cosine theta. So I'm going to leave this ambiguity here. We'll talk a little bit more about it as we go along. There are some subtle reasons for what is the correct sign to use, not just in dx but also in dy. So think some more about it, and then so df is like this, and so in this particular case you will have dx this way and dy this way, and this is the direction of positive x force. So let's look at it here. So what do you all think? Should this be plus or minus? Dx is plus or minus p1 plus p2 over 2 times dy. Should be plus? Minus? Yeah, so we want, if you just take the df, this is positive df, if you just take the component of df along the horizontal axis, you'll get this way, but this is direction of positive x, so you feel like it should be negative. So should we put a negative sign here in this? So how many think it should be positive, how many negative? It's just you don't have to feel bad or good about giving the answer, just let's do a poll. How many think positive? I mean, in life you should think positively, but no, in this question. 1, 2, 3, okay, 4. How many think negative? Okay. How many don't want to think? It's just the morning, so you shouldn't be so tired. Okay, actually in this case, dx will be positive. So somebody who said it's positive, why do you think it should be positive? Yeah, in this particular panel, dy is also negative, right? So it's always 2 minus 1. So y2 minus y1 in this particular sketch, dy is already negative. So if this is negative, if you have positive pressure, this is negative, dx will turn out to be negative, so it's the correct direction for this sketch. So now let's talk about d capital Y. So again you have average pressure times what will come here? Dx, and this is like I'm going to leave this ambiguous, plus or minus. Right, so this is essentially ds sine theta, which will become dx. So that's why we are putting a dx here. Okay, so the df, positive df is this way, the vertical component is downward, and direction of positive y force is this way. Will be along the positive y direction. So this sketch will give a negative y force, which means you would say you should put a negative here, right? So that this turns out to be negative. Is that so? But then it kind of didn't work out that easily with dx. So what do you have to do? Plus or minus? Let's do a poll again. How many think it's positive? Okay, how many think it's negative? Some of you are now too nervous, you don't even want to answer. So in this case dx is positive, x2 minus x1 is already positive in this sketch. So you will have to put a negative sign here in order for this dy to turn out to be negative as per the sketch. So in this case d capital Y is minus P1 plus P2 over 2 times dx. Now this is like, seemed very trivial when you start, but these pluses and minuses can trip you up very quickly. And this is for a panel orientation like this. So if you have a different panel orientation, what will happen? So what will, so things to ponder are, so on an airfoil you can have, this is the kind of panel we were looking at, right? It's facing up and aft. You could have a panel like this, it will face up and forward. You could have a panel like this, it faces down and forward. You could have a panel like this, it faces down and back. In all these cases, will you use plus or minus for dx and dy? So that's the sort of thing to think about, and that will be needed for your programming assignment in homework 1. So for today we'll stop here and we'll resume on Thursday.